Hello viewers, welcome to this episode on periodic properties. In earlier lessons we discussed about size of atom and ionization energy. We have seen that how the size of atom varies when we move along the periodic table, whether we go across the period or we go down the group. We have seen that size of atom decreases when we move along the period, whereas it increases when we move down the group. Similarly, we have seen that ionization energy, how this ionization energy varies when we move along across the period or when we move down the group. We have also learned about what are the various factors on which the magnitude of ionization energy depends. In this continuation, now today we will discuss about electron affinity. This is also one of the periodic properties, and in this electron affinity we will discuss what is electron affinity, what are the factors which determine the electron affinity, and then the variation of electron affinity in the periodic table. So, what is this electron affinity? The electron affinity is the energy change associated with the addition of an electron to an atom in its gaseous state. The more negative the energy is from the addition of an electron, the more the process is favored. Here, if the atom has a tendency to gain the electron, and when it gains the electron, the energy is liberated. In this process of the energy liberation, if the magnitude of energy liberated is high, that shows that this process is favored, and the anion formed by this addition of electron, it will be more stable. This electron affinity is measured only when the atom is in gaseous state. Now, we define the electron affinity. The electron affinity of an element can be defined as the amount of energy released when an electron is added to the valency shell of an isolated neutral gaseous atom of that element. It can be represented as X in gaseous form. This is the atom of the element which is in gaseous form, and when this electron is added to it, it changes into the gaseous ion and energy is liberated. This amount of energy liberated is the electron affinity of that element. Higher the amount of energy liberated, higher will be the electron affinity of the atom. And since the energy is evolved during this process, the electron affinity has a negative sign and is thus it is a exothermic process. Higher the electron affinity of an element, the more energy is given off when an electron is added to an atom of the element. It means that if an atom gains an electron and it changes into ion, higher the amount of energy is liberated, more is the favorable for that process, and more stable will be the ion formed. The magnitude of the electron affinity indicates how tightly an additional electron is bounded to an atom. If higher the value of electron affinity, additional electron is strongly bonded to the atom. That shows that ion has greater stability than its parent atom. Similarly, if the low value of electron affinity shows less amount of energy is liberated during the process, and the additional electron is weakly bounded to that atom. Just as ionization energy is the measure of a tendency of an atom to change into a cation, we have seen earlier that during the process of ionization energy, the amount of energy required to remove an electron, that is the ionization energy, and that measures the tendency of an atom to change into a cation. Similarly, electron affinity of an atom is the measure of the tendency of an atom to change into a cation. If an electron is added to an atom, then an amount of energy is liberated, and how much amount of energy is liberated shows how stable is that anion form. For example, if we take that electron affinity of chlorine atom is 349 kilojoules per mole in gaseous state. This shows that when an chlorine atom in gaseous state gains an electron, then it changes into the chloride ion which is in gaseous form, and 349 kilojoules per mole of energy is liberated. This shows that when an electron is added to a chlorine atom, 349 kilojoules per mole of energy is liberated. This value of 349 kilojoules is very high, and this shows that when chloride atom changes into a chloride ion, the electron affinity value is high and it is most favorable reaction for the formation of the chloride ion. It means when 1 mole or 6.02 into 10 the power 23 atoms or 35.5 gram, which is the atomic weight of the chlorine atom in gaseous state, are converted to the chloride ion, 349 kilojoules of energy is released or liberated, which is the electron affinity of the chlorine atom. So, this way we see that electron affinity measures the stability of the ion formed by the addition of an electron. Now, we move to the next. Here we have seen in this table is of the S block and P block elements, and the values of electron affinities are shown here. These electron affinity values in this table are in kilojoules per mole, and when we see that electron affinity of hydrogen is -73, whereas that helium it is 0. Again we see in the next period of the element or the second period, electron affinity of lithium is -60, then again beryllium it is 0, boron it is 27, next carbon it is 122, again nitrogen it is 0. So, in this period we see the values of electron affinity, and from these values we can find out that the electron affinity value of the 18 group elements or the noble gases it is 0, whereas that of 17 group or halogens, these values are very high. And when we move across the period, we find that there is some irregularities. The value of lithium, for example, is 60, then electron affinity of beryllium is 0, boron it is 27, carbon it is 122, then nitrogen again it is 0, oxygen it increases to 141, then for fluorine it is 328 kilojoules per mole. So, why these values are varying and how these value changes, we have to learn about this. So, these values which we have just seen in the table are the called first electron affinity or EA1 values, since it is related to the addition of one electron to the neutral gaseous atom. These first electron affinity values are called as exothermic electron affinity, because in these values we have seen that energy is released when an electron is added to a neutral gaseous atom, and since the energy is released, therefore, these are exothermic electron affinity values. Now, when we try to add another electron to this uninegative ion, we find that instead of energy released, we have to supply the energy to the anion. Therefore, the second electron affinity values or EA2 of the gaseous uninegative ion is the amount of energy required to add an electron to a uninegative gaseous ion. So, second electron affinity value we have required the energy, whereas in case of first electron affinity value energy is released. So, here we see in this equation that when one electron is added to a gaseous ion, energy is released, and this energy is released is the first electron affinity, and it is shown with the negative sign, since energy is liberated in this process. Whereas, when we try to add another electron to this gaseous uninegative ion, instead of release of energy, we have to supply the energy to this system, and if we have to supply the energy, then this process of addition of second electron to a uninegative gaseous ion is an endothermic process, and in this endothermic process or this second electron affinity value is positive, because we are supplying the energy to the system, and then we get the another binegative gaseous ion, and this in this process energy is supplied, instead of energy is released. So, this equation shows that first electron affinity is an exothermic process. It is shown with the negative sign and energy is released, while the second electron affinity is an endothermic process, and in this process energy is absorbed. Now, we have to find out why the second electron affinity value is an endothermic process, or why the energy is required for second electron affinity. We have seen that when an electron is added to a uninegative gaseous ion, energy is required and is not liberated, because electron is being added against the electrostatic repulsions between the negative charge on the electron and the negative charge on the gaseous uninegative ion. Because in this process, when we try to add an additional electron to the uninegative ion, we have to supply the energies, because there is negative charge repulsions. Due to this repulsions, we have to overcome this repulsion, and for overcoming this repulsion, we have to supply the energy. That is why the electron affinity value of when we add the second electron to a uninegative ion, we have to supply the energy, or this process is the endothermic process. This process is endothermic just to show that there is to overcome the repulsions between a negative charge ion and the negatively charged electron. So, this way the second electron affinity value is the endothermic process, or we require more energy to second electron affinity values. Now, we will see what are the factors which determine the electron affinity, or the factors affecting the magnitude of the electron affinity, because some element has a tendency to gain the electron, and when they gain the electron, different amount of energies were liberated, as we have seen in the earlier table. So, there are number of factors on which the value of electron affinity depends, but the important factors are size of atom, nuclear charge, and electronic configuration of the atoms. These are some of the important factors on which the value of the electron affinity depends. Now, if we take the size of atom, we have seen that size of atom in the periodic table decreases when we move across the period, whereas this increases when we move down the group. In the smaller atoms, the attraction of the nucleus for the electrons to be added is stronger. Therefore, smaller atoms, greater is its electron affinity value, because in smaller atoms the nuclear forces of attractions are very high, and due to this they have a tendency to gain the electron radially, and that is why, for example, in the 17th group or the halogens groups, the size of the atoms are smaller, therefore, they have high value of electron affinity. Then the next factors which determine the electron affinity is the nuclear charge, and greater is the magnitude of the nuclear charge of the element, stronger will be the attraction for the added electron, hence greater will be the value of electron affinity. In the periodic table earlier we have seen that the magnitude of the nuclear charge increases when we move across the period, as well as it increases when we move down the group. Then it also depends on the electronic configuration of the atom. The value of electron affinity of elements is affected by the electronic configuration of the atoms. We can explain this by considering following examples. Now, if we see the elements of second group or 12th group. So, second group elements are beryllium, magnesium, calcium, strontium, barium and radium, and these elements have NS2 electronic configuration, that is, their outermost shell is completely filled and it has 2 electrons in their valency shell. Again, the 12th group elements, these elements are zinc, cadmium and mercury. These elements of the 12th group, they have n-1 d subshell, they have 10 electrons, and whereas their last shell NS shell, it has 2 electrons. That is, they have completely filled their n-1d subshell and completely filled ns orbitals. So, in this type of elements which have completely filled ns orbitals or n-1d orbitals, or we can say that those elements which have completely filled shells, their electron affinity values have very low, because these elements do not accept electrons, or they have a very little tendency to accept the electrons. Since their shells are completely filled, so they have least tendency to accept the electron, and if they have least tendency to accept the electron, their electron affinities values will be very less, or they will be 0. So, the electron affinity of these elements of the second group or 12 group, it is 0 or it is less than 0, that is, no electron is accepted or no energy is released. Rather, they have a tendency to absorb the energy if they have to accept the electron. Therefore, they have very little value, or almost their electron affinity values are 0. Then, on the basis of this electronic configuration, if we see the electronic configuration of nitrogen and phosphorus, we find that in case of nitrogen, its atomic number is 7 and the electronic configuration is 1s2, 2s2, 2p3. Similarly, for the electronic configuration of phosphorus, its atomic number is 15 and in the third shell it has 3s2, 3p3. That is why its p subshell or p orbital is exactly half filled, and we have seen in the case of ionization energies also that elements or atoms which have exactly half filled orbitals, they are very stable. Their ionization energies values was very high. Similarly, in case of electron affinity, since the atom of nitrogen and phosphorus, they are half filled, that is, their np orbital is exactly half filled. So, they are very stable and they have very little tendency to accept the electron. Therefore, their ionization energies values are very low. Now, we come to another class of elements, that is the noble gases. What we find in noble gases, that except helium, which has 1s2 electronic configuration, rest of the noble gases have ns2p6 electronic configuration, and this ns2p6 electronic configuration means their valency shell is completely filled. Since their valency shell is completely filled, they have very little tendency or they have no tendency to accept the electron. Therefore, their ionization values are very low, and this we have seen in the table also, that the noble gases or the 18 group elements, their ionization energies values were 0. Now, we will try to explain the various trends observed in the periodic table for electron affinity. Generally, on moving left to right in a period, we find that the value of electron affinity increases from alkali metals to halogens. Here we see that as the size of atom decreases and the nuclear charge increases, so both these factor increases the force of attraction between the nucleus and the electrons being added. Hence, the atom has greater tendency to accept the electron. On left hand side, alkali metals, they have lowest value, because these alkali metals, their size of atom is large and nuclear charge is also low. But on right hand side, we have halogens which have highest value as they attain the stable noble gas configuration when they gain one electron. So, they have very high value of electron affinity, and these halogens have smallest size as well as high nuclear charge. Therefore, large amount of energy is released when an electron is added to the gaseous atom of these halogens. Therefore, they have high value of electron affinity. Now, variation down the group. When we move down the group, we have seen that both the size as well as nuclear charge increases. The increase in size tends to decrease the electron affinity. When we move down the group, since the additional shells are being added, the size increases, and this increase in size tends to decrease the value of electron affinity. Simultaneously, the charge is also increasing when we move down the group, and we have seen that increase in charge tend to increase the value of electron affinity. So, when we move down the group, the net result effect produced by the progressive increase in the atomic size outweighs the effect produced by the progressive increase in nuclear charge, and with the result the electron affinity goes on decreasing as we move down the group. Because when we move down the group, we have seen that nuclear charge is increasing as well as size of atom is increasing. So, this increase in size of the atom outweigh the effect produced by the progressive increase in the nuclear charge, and therefore, tendency to accept the electron decreases when we move down the group, and when this tendency decreases when we move down the group, naturally the value of electron affinity goes on decreasing when we move down the group. That shows that less amount of energy will be released when an electron is added to the neutral gaseous atom, and this shows that they have less tendency to accept the electron. So, now we will see what is the actual trend observed in the periodic table, that in the second period element the electron affinity of lithium is more than beryllium, though it increases in general, it increases when we move across the period or along the period, but here it decreases, and in case of beryllium we have seen earlier in the table also that electron affinity of beryllium is almost 0. Then it increases to boron, then it goes on increasing to carbon, then again the electron affinity of carbon is more than nitrogen. So, we have seen that it depends on electronic configuration also, and here in case of beryllium the valency shell has NS2 or it is completely filled, therefore, it has least tendency to accept the electron and its electron affinity value is less. Again in case of nitrogen it is exactly half filled, therefore, electron affinity value of nitrogen is 0. Then it increases to oxygen, it increases to fluorine, and then again in noble gases it being completely filled, it is again less or it is almost 0. So, this is the trend in second period which is actually observed. Now, in third period also similarly, though it increases, but in case of magnesium being NS2 shell completely filled, or in case of phosphorus which is exactly half filled, or in case of argon electronic configuration it is completely filled, their electron affinity value are 0. So, this is the actual trend we observed along the period. Now, when we move down the group, say in case of alkali metals, so it goes on increasing as the size of atom is increasing. So, that effect of increase in size overweigh or outweigh the effect produced by the increase in nuclear charge. And in first group elements there is a decrease in value of electron affinity with the increase in size of atom as well as increase in nuclear charge. But in case of 16th group elements, we see that electron affinity value of oxygen is less than sulfur, though in first group we have seen that the electron affinity value of lithium is more than sodium. But in case of this 16th group element, the electron affinity value of sulfur is more than oxygen, whereas oxygen has less value than sulfur, though the size of sulfur is increasing. Similarly, we find in 17th group also, that is the halogens. Here we find that the electron affinity value of chlorine is more than fluorine, though the size is increasing. So, why it is so? Why the electron affinity of fluorine is less than chlorine, or why the electron affinity of oxygen is less than sulfur? So, here we find that due to small size of oxygen and fluorine atoms as compared to size of sulfur and chlorine atom respectively, when an additional electron is added to these shells, second p shell of these atoms, due to increase in electron density, the electron repulsions increases, and due to this increase in electron repulsions, they have less tendency to gain the electron. Due to this reason, the electron affinity value of oxygen and fluorines are less than their next member of their groups, that is sulfur and chlorine. So, that is why the electron affinity value of oxygen and fluorine are less than those of sulfur and chlorine atom respectively. So, this is due to the increased electron-electron repulsions. Oxygen and fluorine atom has less tendency to attract the electron and hence less value of energy is released. Therefore, they have low value of electron affinity. Now, we conclude that what we have learned about electron affinity. We have seen that the electron value of electron affinity depends on various factors. The important were the size of atom, the nuclear charge and the electronic configuration, and all these affect the value of electron affinity. We have seen that in general the value of electron affinity increases when we move across the period, whereas it decreases when we move down the group, but depending on the electronic configuration there were some exceptions, that electron affinity of second group elements or the 12th group elements or the 18th group elements, they have very low values or they have no tendency to accept the electron. So, why they have these values or why they have low values, we have learned about that. Then we have learned why the electron affinity of fluorine or oxygen is less than their next element, that is chlorine or sulfur. So, this is due to the increase in electron repulsions, they have less value of electron affinity. So, in this way we have also seen that the second electron affinity is less than the first electron affinity, and the second electron affinity is a endothermic process, whereas the first electron affinity is an exothermic process. So, in this way we have learned about the electron affinity, and in the next lesson we will learn about the various trends observed or how these values of electron affinity varies in the periodic table. We will like to see that through the graph as well as in the table values of the various elements present in the table. We will also learn in the next lesson how to we determine the electron affinity, and this electron affinity is very difficult to determine, to calculate. So, this value of electron affinity we have find out with the help of Born-Haber cycle. Then we will learn about the electronegativity also in the next lesson, and what is electronegativity and how this electronegativity is determined. We will learn about that in our next